Okay, we'll go ahead and get started. Can you see my screen and hear me okay?
Yeah, we can.
Thank you. So what we're going to do today is we're going to go and review the exam 3 answers and go through that test. And then we'll start on chapter 7. Just to give you a feel for what's up next week is on Monday, we'll complete chapter 7. And then on Wednesday of next week, we'll have a quiz on chapter 7, and we will start the lecture portion of chapter 8. So the first question, energy is consumed when chemical bonds are broken. That's true. Question 2, internal energy of a system is the sum of all kinetic energies of all components of the system. That one was false. It's the sum of the kinetic and the potential energies. Number 3, if the angular momentum quantum number L has a value of 3, it is represented by the letter, and in this case, L equals 3, that means it's F. Number 4, the heat involved with an exothermic process would have a negative sign. That was true. 5, Q and W are state functions. If you recall, Q is heat and W is work. Those are not state functions, so that was false. Number 6, the change in enthalpy, delta H, is the enthalpy of the products minus the enthalpy of the reactants. That one is true. Number 7, the delta E of the system that absorbs 12.4 joules of heat and does 4.2 joules of work on the surrounding is how many joules? For that, you needed to remember that delta E equals Q plus W, so delta E equals heat plus work. The system was absorbing heat, so we don't change the sign on the 12.4 joules from the heat contribution, but the work was done on the surroundings, so that's exothermic, so you needed to change the sign to minus 4.2 joules. So if you did that and then did the math, you got a positive 8.2 joules. Number 8, the value of delta H for the reaction below is minus 790 kilojoules. The enthalpy change accompanying the reaction of 0.95 grams of sulfur is how many kilojoules? So since you were given a gram value, you needed to convert that to moles. So you would have needed to look up the atomic weight of sulfur. That's the 32.066 value in the denominator. So that tells us how many grams per mole. So that converts the 0.95 grams from grams unit to moles unit. Then you needed to go and look at the stoichiometry of the reaction to see how many moles of sulfur were involved. And the answer is 2 because of the 2 coefficient in front of the sulfur. So that tells us that 2 moles of sulfur are involved in this reaction with the minus 790 kilojoules. So the 2 moles of sulfur will be in the denominator so that our moles of sulfur units cancel, and that leaves us with units of kilojoules. And if you work out the math, you get minus 12 kilojoules. Number 9, What is the molar heat capacity of liquid bromine, Br2? And you're given the specific heat of Br2 is 0.226 grams, joules per gram Kelvin. So if you basically you needed to convert grams to moles, so you needed to calculate the molecular weight of Br2. The atomic weight of bromine is 79.904, so you multiply that by 2 to get the 159.808, and then we can convert grams to moles. And if we do that math correctly, we get 36.1 joules per mole Kelvin. In number 10, you're given these two reactions, 2S plus 3O2 going to 2SO3, and you're given a delta H value for that reaction. And then you have S plus O2 going to SO2, and you're given a delta H for that. You want to calculate the enthalpy for this third reaction, 2SO2 plus O2 going to 2SO3. So what you need to do is you need to check those two initial reactions that you're given delta H values for and see if they are written in the right direction, so to speak. And so we see the first reaction, we have SO3 as a product, and in the reaction we're trying to determine the enthalpy on, SO3 is a product. So that one looks okay. The other thing we look at is we look at, do we have the right number of compounds? And so we have 2 SO3 molecules and 2 moles of that in both reactions. So we're good there. We don't need to do anything to that. That reaction is good the way it's written. The second reaction, we see that SO2 is in the product side, so it's on the right side of the equation. For the reaction that we're looking at, we want it in the reactant side, so it needs to be on the left-hand side of our chemical equation. So you would have to flip that reaction around. If you flip it around, remember the delta H numerical value doesn't change, just the sign. So now going from SO2 to S plus O2, that becomes a positive 297 kilojoules. We see that we need 2 moles of SO2, and so we need to multiply that reaction by 2. So now we have minus 790 plus 2 times a positive 297, and we get a minus 196 kilojoules as our answer. If we want to check our equations to make sure they add up to be this reaction that we really want. And so if we go ahead and write them out, the first one's written as it is above. The second one is written flipped and then multiplied by 2 across the board. We can then go and we can cancel out the 2 S's. We can cancel out 2 of the O2s because we have 3 on the reactant side and 2 on the product side. So that leaves us with 1 on the reactant side. And then the 2 SO2 and 2 SO3, those come out the way we want. And when we add that up and we see that our resultant reaction is the same one that we're trying to calculate the enthalpy for. So in this problem, we needed to look at the reactions that we were given to see if they're going the right direction. If they are, great. If not, then we needed to flip them around. And that second one, we needed to flip around. And then we needed to make sure that the coefficients were balancing. And so in the first one, we were fine, but the second one, we needed to multiply by 2 in order to get the coefficients of the final reaction appropriate. And because we had to multiply that by 2, we had to multiply its delta H by 2 as well. So we had a few things going on there in that problem. Number 11, according to the Heisenberg uncertainty principle, it's possible to know precisely both the position and the blank of an electron. That answer is momentum. Number 12, all the orbitals in a given shell have the same value as the which quantum number? That would be n, the principal quantum number. Number 13, which one of the following is not a valid value for the magnetic quantum number of an electron in a 5D subshell? So need to remember that the magnetic quantum number was that m sub L, and minus L to positive L are kind of the choices. And so in this case, the answer for D is L equals 2. And number 14, an electron cannot have the quantum number, and the answer is 1, 1, 1 for the N, L, and M sub L quantum numbers. 15, which of the quantum numbers below represent the principal quantum number? The principal quantum number is N. 16, the Pauli exclusion principle states that no two electrons in the same atom can have the same set of 4 quantum numbers. That's true. 17, which is the correct electron configuration for a nitrogen atom? So that's 1s2, 2s2, 2p3. So you would fill those kind of going across the periodic table as we discussed in class. First the 1s, then the 2s, then the 2p. 18, Hund's rule says that every electron in an atom must differ by at least one of the 4 quantum number values. That's false. Hund's rule talks about having the same spin before pairing. So in other words, as you go across, all the arrows will be pointing up before you start pairing them off. 19, the ground state configuration for fluorine. It's that helium core electron shell, and then 2s2, 2p2, 2p5 rather. So once again, you're just filling the electrons as you go across. 20, the wavelength of light that has a frequency of 1.20 times 10 to the 13 seconds to the minus 1, and you want that expressed in meters. So you needed to remember that the formula is frequency equals speed of light divided by wavelength, and speed of light is 3 times 10 to the 8th meters per second. If you plug those numbers in for the frequency and the speed of light and then solve for wavelength, you get 2.50 times 10 to the minus 5 meters. '21, what's the wavelength in nanometers that has a frequency of 3.22 times 10 to the 14th seconds to the minus 1? Once again, we use that same formula, frequency equals C over wavelength, and plug in the frequency value and the speed of light value, and you'll get an answer of 9.32 times 10 to the minus 7th, but that's in meters. The question asked for the answer in nanometers, so that is equal to 932 nanometers. 22, the wavelength of a photon that has energy of 5.25 times 10 to the minus 19 joules is how many meters? So since we're talking about energy and we want to get to wavelength, we know we're going to have to convert to frequency. And that's where this first formula, energy equals h times frequency, h is Planck's constant. So we have the energy value, the 5.25 times 10 to the minus 19. That's equal to 6.626 times 10 to the minus 34th times the frequency. We can solve that equation for a frequency value. That's the 7.92 times 10 to the 14th value. We can then take that frequency value and use it to convert to wavelength. And that's using the second formula again of frequency equals speed of light over wavelength. And we plug in the frequency value and the speed of light value, and we solve for wavelength. And that comes out to, excuse me, 3.79 times 10 to the minus 7th meters. Number 23, what's the wavelength, this time in angstroms, of a photon that has an energy of 4.38 times 10 to the minus 18 joules? So similar to the previous problem, we're going to use that energy relationship where energy equals h times frequency. And we're going to solve that for the frequency value, and that's 6.61 times 10 to the 15th. Now that we know our frequency, we can use the frequency equals c divided by wavelength to find the wavelength. And so we plug in the speed of light value and the frequency value, and we get a value of 4.54 times 10 to the minus 8th, and that's 454 angstroms. '24, the frequency of electromagnetic radiation required to promote an electron from n equals 2 to n equals 4 in a Bohr hydrogen atom is how many hertz? So we needed to use the formula that tells us delta E equals E final minus E initial, and that equals the constant minus 2.18 times 10 to the minus 18 joules times 1 over the final level squared minus 1 over the initial level squared. So we plug in those final and initial n values. So the final was 4, so it's 1 over 4 squared. The initial was 2, so that's 1 over 2 squared. And then that is times the constant, the minus 2.18 times 10 to the minus 18 joules. If we do that correctly, we get a value, a delta E value of 4.09 times 10 to the minus 19th. But we're not quite done yet because we wanted the answer in hertz and a frequency value. And so then we go back and we use that energy equals h times the frequency. We just solve for the frequency, so we have the 4.09 times 10 to the minus 19 equal to 6.626 times 10 to the minus 34th times the frequency. If we solve for frequency, we get 6.17 times 10 to the 14th. '25, the principal quantum number of the first d subshell, and the answer is 3. So remember, principal quantum number is that n value. 26, each d subshell can accommodate how many electrons? There's 5 of those, and so each has 2 electrons in it, so it's a total of 10. How many quantum numbers are necessary to designate a particular electron in an atom? And the answer is 4. There's four quantum numbers that we use to describe the electrons. 28, what is the correct ground state electron configuration for chromium? So chromium was one of the exceptions that we talked about in class. And so that has that argon noble gas core and then 4s1 3d5. By having it 4s1 3d5 instead of 4s2 3d4, you have 2 half-filled shells, and that's more stable, lower energy. Okay, 29, electromagnetic radiation with a wavelength of 640 nanometers appears as orange light. What's the frequency of this? So we can use that frequency equals c divided by wavelength. The key here is that the wavelength needs to be expressed in meters, since our units on the speed of light are meters per second. So 3 times 10 to the 8th meters per second divided by, and if you're in nanometers and you want meters, an easy way to do that is just make it times 10 to the minus 9th. And so I had divided by 640 times 10 to the minus 9th. And if you do the math, you get a value of 4.69 times 10 to the 14th seconds to the minus 1. Number 30, the symbol for the spin magnetic quantum number is m sub s. And then the final question, the larger the principal quantum number of an orbital, the lower is the energy of the electrons in that orbital. That's false. The higher the principal quantum number, that's that n value, the higher the energy. So overall, people did pretty well on the exam, so that was nice to see. Does anyone have any questions before we move on? Okay, this answer set to the exam is posted on Canvas, so if you want to take a look at it later, you can do that. So what I'm going to do now is I'm going to pull up the lecture, and we will start on, we'll go ahead and start on the next chapter. Okay, can everybody see the slide, chapter 7 slide?
Yes.
Thank you. Okay, so what we're going to talk about in chapter 7 is kind of a follow-up to the lab you did, I guess it was a week or two ago. And so it'll be a little bit different approach than the stuff that we did in the lab. We're going to expand upon some of the periodicity that we see in the periodic table. In the lab, we were concerned mostly about boiling point and melting point and things like that, more physical properties. In this chapter, we'll talk a little bit about that kind of stuff, but we'll also talk about things that I think are a little more applicable when we talk about doing chemistry reactions and taking advantage of some of the properties of the elements. So the periodic table, Mendeleev and Meyer get credit for kind of starting it, although Mendeleev is really the one who gets most of the credit, and we'll talk about that in a moment. One of the things I think is real interesting is here we have a picture of the periodic table with the elements there, and it has kind of color-coded when the different elements were identified. And so I always think it's interesting that if you look at the kind of the light blue ones, and down at the bottom it says that's from 1735 through 1843, and 42 elements were discovered during that time period. And so for me personally, I always think that's pretty interesting that many elements were discovered at a time when the technology really wasn't very sophisticated. So that's impressive to me, that many of the elements could be identified, and without all the tools that we have today to look at some of these things. The other thing I think is interesting is that they were able to piece together, the beginnings of the periodic table in a pretty good way, to the point of where a lot of it is still used to this day. And here's an example of something. So Mendeleev had something in 1871 that he called ecosilicon. And Not really certain what that name means or where it came from, but if you look at the properties that he was able to determine back then, it compares pretty similar to germanium. And germanium wasn't discovered until a number of years later in 1886. So what's impressive about that is, to me, is that he was able to do these measurements and draw some conclusions, even that long ago when he didn't have the tools that we have today. The other thing that's pretty good about Mendeleev is that he was able to predict some elements that hadn't even been discovered yet. And so he identified properties that unknown elements at the time had and said, well, these should fit into certain spots in the periodic table, and he turned out to be correct. So his table was based on atomic mass, because at that time that was a pretty fundamental property that was known about the elements. About 35 years later, when the nuclear atom was discovered, Rutherford introduced those, and then Moseley finally introduced the concept of atomic number, determining that experimentally. And that's became where the number of protons was considered then the basis of the periodic property of the elements. So it's based on atomic number, which links back to those protons. It all kind of started with Mendeleev and the atomic mass approach. So when we talk about periodicity, what are we really talking about? What we're talking about is there's some type of pattern for a property when we look at elements. Maybe it's in a row, maybe it's in a column, things like that. And hopefully when you did the lab, the computer lab, you saw some of that in some of the work that you did, and saw that things would increase or decrease or go up and then go down or something, but it was that repetitive pattern that we call periodicity. We're going to talk about a few of these properties in chapter 7, and what we're going to focus on are sizes of atoms and ions, ionization energy, electron affinity, and then some chemical property trends. So if you think about what you did in the lab, that was more focused on the last one of those bullet points, some group chemical property trends. And so we'll talk a little bit about that, but initially we're going to talk about sizes of atoms and ions and how that fits in terms of periodicity, and then also ionization energy and electron affinity. Ionization energy and electron affinity is pretty interesting stuff, because there's a discipline called mass spectrometry that's used quite heavily in the analytical chemistry world. And a lot of that is really based upon ionization energies and electron affinities and things like that. So that's a real important property that the elements have. So the first thing we're going to talk about is something called effective nuclear charge. So let's see what that's about. So what you'll see is that a lot of the properties depend on attractions between the valence electrons in the nucleus. So remember when we talked about the atom, we talked about how there's that nucleus in the middle, and that's where the protons are. And hopefully remember that the protons are positively charged. Then you have the core shell of electrons around it. And so when we were doing our electron configurations, we often represented that by that noble gas symbol and said those were the core electrons. And then the electrons that were past that noble gas, those were the valence electrons. And so this picture on the right of a sodium atom is a pretty good representation of that. So we have the sodium nucleus with 11 protons in it. Then we have 10 core electrons. And so that's that noble gas configuration. And then finally, we have one valence electron for sodium that's in the 3s region, 3s orbital. So we have that region of valence electrons, we have the core electrons, we have the nucleus. So remember, the nucleus is positively charged, the electrons are negatively charged. So we've talked about this before, but we say that opposites attract. So you've got an attraction there between those electrons and the protons. The other thing that happens, though, is the electrons are both negatively charged, whether it be the core or the valence electrons. And so you have some repulsion going on there. So the electrons are kind of attracted to the nucleus because of the positive protons there, but then they're also being repelled by the other electrons. And so this attraction is decreased by that electron-electron repulsion. So there's this kind of back and forth battle going on between the attraction of the nucleus to the electrons and then electron-electron repulsions. So there's this balance of all this that produces the effective nuclear charge. The other interesting thing about the effective nuclear charge is, even though it's a pretty complicated thing that's going on, you can actually get some pretty good approximations of it through a pretty simple formula. And that's what we're going to take a look at here, is the effective nuclear charge can be expressed as Z minus S. Z is simply the atomic number of the atom, and S is something called a screening constant. The interesting thing about the screening constant, there's different ways you can calculate it, some more complicated than others, but a real simple way to calculate the screening constant is simply to count the number of inner electrons. So in other words, if you count the number of electrons that would be in the atom's noble metal configuration, if we're doing that electron configuration, that's a reasonable approximation of S. And so then you would subtract that S value from the atomic number to get that effective nuclear charge. So effective nuclear charge is a periodic property. It increases as you go across a period. Remember, going across a period means going across a row, and it increases slightly, not as much, but slightly as you go down a group. So in other words, start from the top and go down. This plot on the right-hand side is kind of interesting because it shows some different ways that this effective nuclear charge can be calculated. And what you see is even though there are some pretty sophisticated methods to calculate it, you can get reasonable agreement between those sophisticated ways of doing the calculation and our simpler ways, such as this effective nuclear charge equation that we just discussed, and then something else called Slater's rules, which we'll talk about in a bit. So let's talk about the size of an atom. When we talk about the size of an atom, we talk about a non-bonding atomic radius, which is also referred to as van der Waals radius. And this is half of the shortest distance separating two nuclei during a collision of atoms. So in other words, it's not bonding or anything, it's just when the atoms collide. There's also something called the bonding atomic radius or the covalent radius. And this is half the distance between nuclei in a bond. That's really the one we're most interested in. Because usually when we're talking about things, we're trying to figure out what's going on from a bonding perspective. So we're going to focus more on the bonding or covalent radius than we are this non-bonding atomic radius or van der Waals radius. So let's take a look at the picture for a moment here, and we can get a visual of what we're talking about. So we see there on the right, that arrow shows the non-bonding atomic radius. So in other words, in non-bonding, the atom is kind of sitting there and it's just from the nucleus to the outer end of it. Then we have we see the distance between the nuclei, and we see that because this is a bonding situation, we see now that they're kind of mushed together is the way I think of it. And so that bonding atomic radius is half of that distance from the nucleus of one atom to the other. So the nuclei can't get closer than what we see in that bonding atomic radius situation because of that repulsion of core electrons on the neighboring atoms. So when we talk bonding, and we'll learn more about this as we go on, we're usually talking about interactions of those valence electrons. And so we can do some things with that, but as they get closer together, and then the core electrons in the atoms kind of take over, and then that's where we kind of reach the limitation of how close things can be. Because remember, we talked about how there's an electron repulsion going on in addition to that attraction to the nucleus, positively charged nucleus. So let's take a look at the size of atoms and see how that varies according to the periodic table. So the figure below shows that there is a trend in bonding atomic radius. So remember, bonding atomic radius, again, is this second one. That's the one we're real interested in. And so what we see is that the bonding atomic radius in general decreases as we go from left to right across a period. So in other words, if we started with potassium and then calcium and then went on down all the way over as we get to arsenic, selenium, bromine, and that, we see that it is decreasing. We see that the bonding atomic radius is decreasing. And this is because we have an increase in effective nuclear charge. So if we sat down and did that calculation that we talked about to get an effective nuclear charge, we see that is going up. And so that means the atomic radius, the bonding atomic radius, is going down. This is because we're now having the valence electrons get closer to the nucleus, and this causes the bonding atomic radius to decrease. As we go from top to bottom in a group, so in other words, if we're in, say, in the 1A or 2A and went down, we see that there's a slight increase in the we see there's a slight increase in the size. And this is because we're getting an increase in that principal quantum number n. Remember, we talked about how the principal quantum number, that would be the 1, the 2, the 3, the 4 on down the line, that's telling us that we're adding essentially layers of electrons on top of it. So it's just getting bigger. And so as it gets bigger, those outer electrons are farther from the nucleus. And so then it becomes a bigger size of the atom. So what we see is change in size, that there is periodicity to it, and we see that it's linked back to effective nuclear charge and then increasing quantum numbers. So let's talk about ions for a moment. And so we determine that the interatomic distances in ionic compounds, and that's how we determine the size of the ion. So they're in some type of ionic compound, and we see what those distances are. The ionic size depends on a few things. It depends on the nuclear charge, it depends on the number of electrons, and it depends on the orbitals in which the electrons reside. So all those kind of go together. The other thing you'll notice in this picture is, so the red ones are cations, and then the yellow are the associated neutral atoms. and the blue ones are anions. What you see is that the cations are consistently smaller than the neutral atoms, and the anions are consistently bigger than the neutral ions. And why is that? Well, if we recall, if something is forming a cation, what is happening? Well, it's losing an electron. Okay, so losing an electron, so that's going to give us fewer electrons, so that there's a loss there. So it becomes smaller. The other thing is when you lose those electrons, then you have less electron repulsion and more of that opposite attract thing happening. So it makes it smaller. On the other hand, with the anions, we think of what happens when an anion forms. Those atoms have picked up electrons. So we have the opposite effect. We have more electrons. So we've added more electrons to that outer shell. And then we've also having now more electron repulsion. So it can't pack in as tightly with that positive nucleus. So this is kind of a repeat of what I just said, is that cations are smaller than their parent atoms. You've removed some outer electrons, some valence electrons, and that reduces the electron repulsion. And then anions are typically larger than their parent atoms because you've added some valence electrons to make it bigger. And then now, because of those additional electrons, you have more electron repulsion going on, and those combine to make it bigger. So what you see on a lot of this stuff is what you're talking about how the electrons interact with each other and how they react with the positively charged protons. When you have ions that have the same number of electrons, that's called an isoelectronic series. And what you find is that the ionic size decreases as you increase the nuclear charge. So below we have an isoelectronic series where each of these ions has 10 electrons. So let's take a look at that. So we have O-2, we have negatively charged fluorine, we have Na+, Mg+2, and aluminum +3. So each of those, if you counted up the electrons, would have 10 electrons in it. And we see down at the bottom, the ionic radius is getting smaller as the number of protons increases. So the protons go from 8 to 9, then 11, 12, 13. And so what happens is you're increasing the nuclear charge as you go with these more protons, the same number of electrons. You get a decreasing ionic radius as the number increases. Well, why is that? Well, one big reason is if we compare the -2 oxygen to the +3 aluminum, well, in the -2 oxygen, we've got those 10 electrons, but only 8 protons. With the aluminum +3, we've got 13 protons now and 10 electrons. So you can think of it as you have more positive charge in that nucleus. And so you're going to have more attraction of those electrons, be more tightly attracted, more tightly bound to the nucleus. And so then that results in the size of the ion being smaller. So even though the electrons are the same, that stronger positive component, because of the additional protons, cause things to compress. It's probably the easiest way to think of it. So once again, we get a periodic type trend that we see in terms of this case, an isoelectronic series. And it's because, once again, of interactions of electrons with each other and electrons with the protons. So we talked about a real simple way to do effective nuclear charge. And that was that atomic number minus basically the number of core electrons. There's another way to do the calculation, which is a little more sophisticated, but still not too difficult. And so I'd like to go over that. And that's using something called Slater's rules. So Slater's rules can be used to calculate the effective nuclear charge for elements that do not have D or F subshells. So remember that if you have a D or F subshell involved, Slater's rules don't apply. It's only good for elements that don't have a D or F subshell. So it is somewhat limited, but it is another way to kind of estimate what that screening constant value is, S. And it's a little bit more sophisticated than strictly just looking at those core shell electrons. So the rules, Slater's rules say that electrons for which the principal quantum number is larger than the value of n for the electron of interest, those contribute 0. So that makes sense. If I'm looking at an electron that is, say, a 1s or 2s or something like that electron, and there's electrons that are at the 3s level, for instance, well, that's outside of where I'm at. So it's not going to shield that proton, that nucleus area. So it makes sense that those would have 0 contribution. So electrons with the same value of n, remember once again, n's that principal quantum number, same value of n as the electron of interest, contribute 0.35. Electrons with a value of n minus 1 contribute 0.85, and then electrons with a value smaller than n minus 1, contribute 1. So all that's saying is the closer the electron is to the nucleus, the more contribution it has. Whereas before we were just saying all those core electrons were the same. So it's a little bit of a tweak to that original premise that we discussed. We'll do a couple examples here in a moment, and I think it'll be a little more clear after that. So if we take fluorine as an example, there are 9 total electrons in fluorine. You have 2 1s electrons, 2 2s electrons, and 5 2p electrons. So for a valence electron in fluorine, so in other words, in this case, the valence electron would be one of those 2p electrons. Let's take a look at what we would get for that. So we have 6 times the 0.35. Remember, we said 0.35 is the value we use for electrons of the same value of n as the electron of interest. So we said we had 2 2s and 5 2p. So that's 7 electrons that are in that n equals 2 shell. Well, why aren't we using 7 instead of, and why are we using 6 instead of 7? Well, that's because we don't count the electron that we're studying. So there's 7 valence electrons there, the 2s and the 5 2p, but we're not going to count the one that we're trying to calculate the shielding constant for. So that's why that's 6. And so those are the 2 n equals 2 electrons. Then we have 2 1s electrons. Going back, we said electrons with a value of n minus 1 contribute 0.85. So n minus 1, 2 minus 1 is 1. So we have 2 of those 1s electrons. So that gives us 2 times the 0.85. So we do 6 times 0.35 plus 2 times 0.85, and we get a total of 3.8 as our new shielding constant. So our value then would be 9, our atomic number, minus 3.8 equals 5.2. So slightly different than what we would have gotten if we would have just subtracted those core electrons. So let's go over a couple of homework problems, just to make sure you understand what we're talking about. So let me get the question here. Okay, the first one I'd like to take a look at is 7.15. So they talk about how for sodium and potassium ions, the Z effective number has been determined to be 2.51 for sodium and 3.49 for potassium. And so what do we think, what do we estimate it to be for the outermost electron in both of these, assuming using our initial equation of Z minus S? So for sodium, we would look up the atomic number for that and see that that's 11. Then we would look at the periodic table and determine how many of those core electrons are there. And that answer is 10. And then we'd have 11 minus 10 equals 1. A similar approach for the potassium, we'd see that that's 19. There's 18 core electrons there, and we get a value of 1. So that was using that simpler approach that we talked about, the real basic one of which just atomic number minus the number of core electrons. Those core electrons are the number of electrons if we look at that noble gas configuration portion of the electron configuration for the atom. In part B, what would this value be, the Z effective value be, if we use Slater's rules? So for Slater's rules, what we need to do is we want to write out the electron configuration. So for sodium, that would be 1s2, 2s2, 2p2, 2p6, 3s1. And then we would apply the Slater's rules. We would go and say, well, how many electrons do we have in the shell that we are? In this case, 3. Well, the answer is 0 because we're looking at that electron. We're looking at the 3-level electron, but there are no others, and it doesn't shield itself. So that's where we do 1 less than the number there. Then we say, well, how many electrons are in that N-1 shell? And so that's the 2 energy level. So that we have 6 from the 2p orbitals and 2 from the 2s orbitals. So that's a total of 8. So we would have 0.85 times 8. And then finally, we have those fully shielding inner electrons. That's the 1s orbital. And we have 2 electrons there. So that's 1 times 2. If we do that math to calculate the shielding constant S, it's 8.8. And we see that the Z effective is 2.2. 11 minus 8.8 equals 2.2. That's using the Slater rules. A similar thing we would do with the potassium. We'd write out that electron configuration. We'd have 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. We go through a similar exercise again. We look for the number of electrons with the same principal quantum number in. We only have 1 electron in the 4 level. And so once again, it doesn't shield itself. So that's a 0. So 0 times 0.35. Then we look at the number of electrons with n-1. In this case, we have 6 3p electrons and 2 3s electrons. So we have a total of 8 electrons in the 3 level. So it's 8 times 0.85 for that contribution. And then finally, in the n-2 or more level, we have the 1 level, and we have 2 electrons in the 1s group. So so that one should act, okay, so excuse me, we have the 2 and the 1. So we have 6 for 2p and 2 for 2s and 2 for 1s. So that's a total of 10 there. We have the 2s and the 1s. Sorry about that. And that's where we get a total of 10 electrons there and that fully shielding 1 value. So we would have 0 electrons from that 4 level, 8 electrons from the 3 level, and then 10 electrons from the 2 and 1 levels. And we add those up and we get 16.8 as our shielding constant. And interestingly enough, we subtract that from the atomic number and we get 2.2 as the value. So in part C of the question, we were asked, which approach gives the more accurate? Well, we go back and we see that in theory, not in theory, but in the actual calculation, we said it was 2.51 for sodium. The Slater gives us 2.2. That's pretty close to 2.51. Potassium, 3.49. Slater, once again, gave that 2.2. Not as good of an agreement, but 2.2 is certainly closer than 1. So the Slater's rules for these two atoms gave us a little bit better, gave us a really good number for the sodium and a better number for the potassium. D says, does either method of approximation account for the gradual increase in Z effective that occurs moving down a group? And no, it doesn't. So both of them gave the same value, even though our periodicity tells us that they should be slightly different. Okay, and finally in E, predict the Z effective for the outermost electrons in rubidium based on the calculations for sodium and potassium. So if we simply look at those and we see that going from sodium to potassium, it was about an increase of 1. We went from roughly 2.5 to 3.5. And then, so that would be a reasonable guess that rubidium would go to 4.5. So what I would ask you to do is go back and take a look at these other homework problems, spend some time on them and get comfortable doing the Z effective calculations, either the simple way and also with the Slater's rules way. So this kind of summary of the Slater's rule down here at the bottom is what you should know. Okay, so let's talk a little bit about ionization energy. So ionization energy is the amount of energy needed to remove an electron from a ground state gaseous atom or ion. And this concept of ionization energy and how much energy you need to put into something to remove an electron from the ground state is really important in the area of something called mass spectrometry. So mass spectrometry, if you ever see anything in the news about, they say there's a certain amount of part per million or part per billion of a substance in something, and you think, well, gosh, how did they do that analysis? Almost certainly it used mass spectrometry, and that involves then creating an ion in the gas phase, and ionization energy is a big part of understanding how to do that. So there's different ionization energies. The first ionization energy is the amount of energy you need to put into something to remove the first electron. The second ionization energy, as you might guess, is the amount of energy to remove the second electron. It always requires more energy to remove that second electron than the first. And the higher the ionization energy, the higher that value is, the more difficult it is to remove an electron. So understanding how easy it is to remove those electrons, in other words, does it have a high or low ionization energy, is important in understanding how difficult it is, or what energy you need to put into a system in order to create that ion. So ionization energy, once again, the amount of energy you need to remove an electron from that gaseous atom or ion. As I said, with each successive electron that you remove, it requires more energy. So it's not the same amount of energy every time. It's more energy each time. And you think about that, kind of think back to that isoelectronic example that we had, and that kind of helps you understand a little bit. As we remove the electrons, then we're removing some of the electron repulsion. We're going to get more attraction to the positively charged nucleus, those protons there. So that makes sense that it would take a little bit more after we take one electron off to get the next valence electron removed. Once you get the valence electrons removed, and then you get to the core electrons, it's even more difficult to get those inner shell, those core electrons removed. And that's really, that you typically don't do that. You typically are only fooling with the valence shell electrons. And that's kind of a common theme. And we talked about this when we were discussing the electron configurations, is that if you're talking reaction chemistry, if you're talking ionization type processes, any of this stuff, you're usually talking about interactions with the valence electrons. That's kind of where all the action is. And so no different here where we're talking about ionization energies. It's much easier to ionize things if you're dealing with valence electrons than it is if you're trying to remove a core or an inner shell electron. There are some periodic trends with the first ionization energy. As you go across a period, so in other words, as you go across a row, it gets more difficult to remove an electron. And so the ionization energy increases as you go across the periodic table in a row, and it generally decreases as you go down a group. The S and P block elements show a larger range of values for the ionization energy, so you see bigger differences there. D block elements, you see some increases, but it's a slower increase. And for F block elements, you don't see much difference at all in the ionization energies. So what are some of the factors that influence the ionization energy? So that effective nuclear charge, that Z effective, and impacts it, and the distance of the electron from the nucleus impacts it. And so as you increase the effective nuclear charge, or you decrease the distance from the nucleus, you increase the attraction between the electron and the nucleus. If you have a greater attraction between the electron and the nucleus, then you need higher ionization energies. In other words, if that attraction is increased, that positive, negative attraction is increased, then it takes more energy to free that electron. And so once again, you increase the effective nuclear charge, or you decrease the distance. That decreases the distance from the nucleus, and it increases the attraction between the electron and the nucleus, resulting in a higher ionization energy. If you think of that, so anyway, there are some irregularities in the general trend. The trend is not followed when the added valence electron in the next element either enters a new sublevel, so in other words, a higher energy sublevel, or is the first electron to pair in one orbital of the sublevel. So in other words, that electron repulsion lowers the energy. And here's an example of that with nitrogen and then oxygen. So you see in oxygen, you're starting to get that pairing, and so that lowers the energy a bit. Let's talk a few moments about electron configurations of ions. For cations, remember with cations, we're losing electrons to form a cation. When we lose those electrons, they come from the highest energy level. And so that means the highest N value. So for lithium, you have 1s2, and then you start filling the 2s level. So if you lose an electron there, it comes from that 2s level, not the 1s level. For iron plus 2, you have a configuration there of 1s2, 2s2, 2p6, 3s2, 3p6, 3d6, and then you'd have 4s2. You lose 2 electrons there, you're going to lose electrons out of that 4s level. And so, because that's the highest N value in its electron configuration. So cations, once again, it's positively charged, so you're losing electrons. Those electrons are lost from that highest energy level. In other words, the highest N value when we look at our electron configuration. Anions, if we have an anion forming, then that means it's picking up electrons, it's gaining electrons. And so the electron configurations are filled to Ns2 and Np6. So if we take fluorine, negatively charged fluorine as an example, we have 1s2, 2s2, 2p6. So we gain 1 electron in the 2p level. So once again, for ions, those electron configurations, cations are losing electrons. They're lost from the highest N value. Anions are gaining electrons. And it'll be filled according to Ns2 and P6. So we talked a moment ago about ionization energy. And we said ionization energy is the amount of energy required to remove an electron. Okay, so now if there's something to lose electrons, then there's also something called electron affinity. And that's the energy change that you get when you add an electron to a gaseous atom. So the example here is we have chlorine plus an electron to give us chloride ion. When that happens, when you pick up that electron, energy is released. since energy is released, if energy is given off, we know that that's exothermic, and we know that that energy flow, that heat flow is negative. So once again, ionization energy is that energy change when we lose an electron, and that, since we're losing it, it's absorbing energy to lose that electron, then that's endothermic, and that's a positive process. By comparison, electron affinity is where we pick up an electron, and so energy is released there, so that's exothermic. So when we talk about the general trends in electron affinity, what we see is there's not a lot of difference in a group. So you see, for instance, the 1A group, minus 73, minus 60, minus 53, minus 48, minus 7, a little bit of change there, but not huge differences. They're all kind of the same order of magnitude type differences. Same with 3A, those are all about the same. 4A, 6A, don't see big differences there. As we go across the periodic table, we see that in general it increases. There are some exceptions. So the 2As, the S sublevel is full. The 5A, the P sublevel is full. And the 8A, the P sublevel is full. So because of that, because you get full sublevels, it kind of disrupts the periodicity a bit. If you see an electron affinity that's positive, what that means is that picking up that electron, it's unstable. And so what that means is you don't see the anions. And so the electron just doesn't happen, and so you don't see pickups of electrons there. So the ones that say greater than 0, that's just telling you that those really, for all practical purposes, don't exist. Okay, so there's a little bit of homework associated with this portion. I think I'm going to stop there for today, unless anyone has any questions. Just to remind you again, on Monday, we'll go ahead and we'll complete the chapter 7. And then on Wednesday of next week, you'll have a quiz on chapter 7, and then we'll start on chapter 8. Any questions before we end? Okay, thank you.